Okay, so my talk is about backing off from infinity. Basically, how do we get fundamental communication results when we're outside of asymptotic regimes? And the first thing to ask is, by the way, since this is a school, I'm going to ask you guys questions. I'm not just going to lecture and talk to my students. No, I also learn people's names throughout the course, but I won't do that to you guys. So anyway. Okay, so what are asymptotic regimes that, for example, Shannon used in the paper that Sergio presented this morning? There's one big one that he even mentioned. What's asymptotic about Shannon's results? Block length. Okay, so what does infinite block length mean in practice? Delay and complexity. Okay, so nobody uses anything that looks like Shannon codes in practice because the delay is too big and the complexity isn't something you can put in a chip. But that's just one asymptotic regime. There's many other asymptotic regimes, all of which are not consistent with what we actually use in practical communication systems today. So what I want to do in the hour and a half roughly that we have is talk about some of these asymptotic regimes, how looking at fundamental results in asymptopia, as we call it, can lead to some misleading results, and how there's been kind of recent research on backing off from infinity, backing out of asymptopia, and getting fundamental results or bounds that actually have more meaning and more insight in practice. Because at the end of the day, even though Shannon theory is beautiful and information theory is beautiful, and it's a very fun area to do research in, many of us, myself included, are really motivated by the practical insights that we get out of information theory in order to understand how to design practical systems. So many people have worked on the results, so I'm just the messenger. These people did all the work, and I'll mention them as I go along in terms of the specific results that people presented. And some of these people are here today. Yuksen Chen and Andrea Goldsmith. So if you have really hard questions, of course, they will have to answer them, not me. Okay, so what is this notion of information theory and asymptopia? Really, in many ways, Shannon's brilliance, well, there were many dimensions of his brilliance, but the notion of coming up with asymptotically long codes, which in particular meant the notion of asymptotically small error, was brilliant, and it led to many things. For example, separation of source and channel coding. So basically, the way that we continue to design communication systems today is we come up with really sophisticated source codes, whether they're lossless or lossy, and then we transmit them over channels using channel codes that try to drive the error probability lower. And we rarely look at the interplay between source and channel coding, which is unfortunate because there is a lot of interesting interplay between source and channel coding, but because in Shannon's case, his result said the error on the channel goes to 0, you don't need to look at the interplay between the channel and the source because the channel is driving the rate to 0. So in some ways, this notion of looking at asymptotically long codes has been enabling. It has brought us a lot of insight, but it's also been limiting. Okay, so how would you think it's been a limiting factor in looking at information theory and its application to practical systems? Or impractical systems even.
Separation theory.
Okay, so separation theory, I know his name, Amir, yes? So what do you mean with separation theory?
No longer holds when you block it, it's fine.
Right, so as soon as you go to finite block length, and I have one slide on finite block length results, and only one because two of the experts on that topic are in this room, and they're students and postdocs, and I don't want to say things that are incorrect, so I'm just going to present the results and talk to them if you have more questions. But separation doesn't hold as soon as you go to finite block length. Because when the channel is introducing a non-trivial number of errors, you need to look at the impact of that on the source. It also doesn't hold, and I have some slides on this because I know something about it, when you look at MIMO systems. So we know about the famous diversity multiplexing trade-off, where you use some antennas for multiplexing and some for diversity. But how should you use those antennas when you're looking at sending a source over that particular channel? Because multiplexing gives you higher data rates, which means you don't need to compress as much. And diversity gives you more robustness, so you get fewer errors. So which is better? It depends on the source. Okay? So this notion of driving error probability to 0 and having infinite delay has been limited. In particular, it's led to what's known as the unconsummated union between networks and information theory. Does anybody know what that means? And feel free to speculate as widely as you like, or where this notion came from, of this unconsummated union. All too young. Any ideas? Okay, no? So what, if you had to say like 80% of papers on networks, theoretical papers on networks, are about what? Or it's a trade-off between what two things? Delay and throughput, exactly. Or queuing theory, okay? All this beautiful queuing theory is all about studying the impact of queues on delays or throughput delay trade-offs. Okay, so much of theoretical analysis of networks is based on the notion of delay. And yet Shannon theory throws delay out the window, infinite delay. Just on the channel code, forget about the network or multi-hop network. Okay, so this notion was coined in a beautiful paper by Bruce Hayek and Tony Ephraimidis from about 20 years ago with the title Unconsummated Union. I think the majority of people only read the title, and that's why it's so famous, because it's a funny title. But it really talked about this notion that Shannon theory is focused on driving error probability to 0 with infinitely long block codes. Queuing theory is focused on a completely different thing. And how do you bring them together? You need to somehow bring delay into Shannon theory. And so you need to expand Shannon theory to look at finite block length, which I'm going to talk about next. Okay? In addition, optimal compression is also based on notions of asymptotically long sequences, as we heard this morning, notions of entropy, and that's what gives you the optimality of separation. Whether you're doing, so what do you do from an information theoretic perspective if you have a source whose entropy is higher than the capacity of the channel? How do you get that source over the channel to the destination? What source and channel coding do you do? In an optimal sense. Hint is that separation holds in an optimal sense for the types of channels and sources I'm talking about. Okay, I'll take a vote. How many people think that you allow the channel to introduce errors? So you transmit at a rate above capacity, raise your hand. Okay. How many people think you transmit at a rate below capacity, raise your hand. Okay, you're right. Okay. From results going back to the Cheeser and Porter book, the way that you transmit a source over a channel is if the entropy of the source is below the channel capacity, you do optimal channel or optimal source compression, compress the source down to the entropy rate, and then you send it over the channel with no errors, because you can send it a rate below capacity over the channel with no errors. That's where the separation theorem comes from, and that's optimal. But it's also true if the rate of the source is below the channel, is above channel capacity, you do the same thing. You introduce distortion, because there's no way you can't introduce distortion, but you introduce the distortion in the source. You still transmit over the channel at capacity, okay? So the channel doesn't introduce errors, and all the distortion, all the errors are introduced in the source code. You compress the source down to a rate below capacity, okay? Now, again, this is all in asymptopia because you're assuming asymptotically long sequences. What happens when you have delay constraints? All that goes out the window, and that's why separation doesn't hold under delay constraints or under finite block length coding, as I'll show in the next next slide. Okay, but now this is all just talking about Shannon's asymptotic world of infinite delay. Okay, but there's many other forms of asymptopia and many results that have come out on, for example, infinite SNR. Give me one example of an infinite SNR result. Anyone? Infinite SNR fundamental. I'm sorry, degrees of freedom, right. The diversity multiplexing trade-off assumes infinite SNR. Any others? What's infinite constellations, because you can't get infinite constellations unless you have infinite. One more example. How about interference alignment? Is also an infinite SNR result. Okay? So, what about under infinite energy? So, what's, okay, do communication systems today, your cell phone, operate under infinite energy? Or finite energy? Well, if it was finite, you wouldn't have to keep recharging the darn thing, right? So basically, it is infinite energy because you're sending it bits per second. Okay? Whenever you send it bits per second, that implies an infinite number of bits that you're sending, which means infinite energy. Okay? And that's why you need to keep recharging your cell phone. What are some examples of systems where you don't have infinite energy? Can't recharge. Sensor networks, okay? Very obvious. If you're going to embed sensors in a bridge or in a person where you can't get energy into that sensor, you need to look at finite energy communication. And that, again, is completely different from what Shannon looked at, because if you have infinitely long block codes, you have infinite energy. And even the beautiful Verdu result on finite energy per bit assumes infinite block codes. It's not a finite block length result. It's an infinite block length result. Minimum energy per bit in an infinite block length. Okay, but that does mean infinite energy. Okay, so there's many systems that don't have infinite energy, and we need to come up with new paradigms for looking at those types of systems. Sampling, we always assume that we sample at the Nyquist rate, but if you look at what's going on in wireless systems today, they're getting wider and wider bandwidths, and as we go to something like software-defined radios, where you span the entire spectrum from DC to daylight, there's no way you can build the hardware to sample at the Nyquist rate. And so you maybe need to sample below the Nyquist rate. And well, how does that impact channel capacity? So I'll talk about that. Things like infinite precision. Actually, when you convert an analog signal to a digital signal, there's finite precision because you don't have an infinite number of quantized bits. And often with feedback, we assume infinite feedback, that we just have a wire from the receiver to the transmitter that conveys whatever was received perfectly with no delay back at the transmitter. So there's many, many assumptions that we make in coming up with fundamental limits. And the real key to doing research is figuring out which one of these asymptotic assumptions give me good insight and which ones don't. Because we always have to make assumptions in doing research. If I would never stand up here and say, well, you should go out and look at all the assumptions that they make in building a cell phone or building a practical communication system, because you would never come up with anything fundamental. There's too many constraints. So you really do want to make approximations and look at asymptotic limits, but understand the implications of those limits in terms of the insights that you get from them. And again, that's what I'm hoping to convey in the discussion today. So, okay. So that should give you the answers to why am I even wasting the next hour and 10 minutes of your time talking about backing off and infinity. Why should we look at backing off? We have such beautiful results in asymptopia. Why should we look at backing off? Someone who hasn't said anything. Or I'll start before me. Practical systems, exactly. So theory, well, okay. So for sure, practical systems aren't going to live in asymptopia, right? But that's okay if the theory that we're deriving is giving us the right insights. Because as long as we're getting the right insights into how to design practical systems from our theoretical results, theory is doing what we want it to do. But if theory is not informing practice, if the practical assumptions that inhibit designing real systems are so far away from the theoretical assumptions that we're making, then we can derive all the beautiful theorems we want, we can publish lots of papers, we can get tenure, and fame and fortune within the information theory community. Well, there's no fortune in the information theory community, but fame anyway. But, but our results will not have impact. And Shannon and some of the most important information theorists, the people I respect the most, Shannon and Gallagher, all of their results were driven by practical systems. Even Shannon, he got a lot of his ideas from working on communication in military systems. So it's important to understand how the theory that you're developing may or may not impact practical systems. And just to give you some examples, okay, theory versus practice. Practice is just taken from the LTE cellular standard. It's the most recent cellular standard. And what constraints are imposed on the systems for that. And of course, I could have taken another example, but that's one of the most sophisticated wireless systems. And this is theory. So infinite block length codes, if you look at practical systems, not just cellular, but other things, sometimes we don't use any codes at all. Uncoded transmission, especially if there are complexity constraints in the receiver, so you can't run a sophisticated decoder. You may have uncoded transmission. LDPC is the most sophisticated channel codes we have today, and you could say, well wait, but didn't Gallagher come up in his master's thesis with LDPC codes? He did. But those actually aren't the LDPC codes that are used in practice. They're a little bit different, and I'll talk about that at the end of my talk when I describe energy constraints on coding. Not just transmit energy constraints, but receive energy constraints. Infinite SNR, so we already mentioned a few examples of beautiful theoretical results under infinite SNR. What's the SNR requirement in LTE? -7 dB. It's amazing that we can communicate at -7 dB. All right, so if we're coming up with beautiful theoretical results for cellular systems at infinite SNR, and these systems are operating in practice at -7 dB, it's not very likely that the theory is going to be informing the practice in that case. Infinite energy, I already said there's finite battery life. That can be okay if you have to recharge, but there's systems that don't recharge. Infinite feedback. So again, we don't have a lot of results on capacity under feedback, any type of feedback. And I'll go into that a little bit later. But most of the results we do have assume infinite feedback, that you basically, there's no constraints on the rate, there's no noise. And, okay, in practice, what feedback do we use? 1-bit ARQ, 1 bit. Okay, so we're about as far from the theoretical results as we can be. Moreover, why do we use 1-bit ARQ? Is there any theory that tells you that that's a good thing to do from a feedback perspective? Anyone know of any results like that? I haven't seen it. Okay, so this is again a case where theory, and 1-bit ARQ is pretty powerful. It's used in so many different types of systems. And yet there's no theoretical results saying it's good, it's bad, it's okay. It's just used in practice. So it would be nice to be able to close this gap a little bit more between theory and practice. Infinite sampling rates, I already mentioned, we assume we sample at the Nyquist rate. Practical A to D converters go up to maybe 500 megasamples per second. So that'll get us, what's the maximum bandwidth that we can, this is a simple question, what's the maximum bandwidth that we can perfectly sample at this rate with no distortion? It's maximum bandwidth signal. Even the undergrads should know this. Oh, come on, this is easy. Nyquist sampling theorem. Half the sampling rate. Okay. Come on, don't be shy. Someone said, just shout it out. Yair. He's the signal processing expert.
What's the question?
You're fired. No. So, Nyquist sampling theorem says that you have to sample at twice the signal bandwidth to recreate the signal with no distortion. So if I'm sampling at 500, say, megasamples per symbol, it's about 250 megahertz is the maximum bandwidth.
Just wanted to check if you know.
Yeah. Anyway, so 250 megahertz, that sounds like a lot. LTE is maybe 20, maybe 40 megahertz. But you look at UWB systems, they're in the gigahertz bandwidths. Okay, and you look at some of these software-defined radios or cognitive radios that need to span the whole spectrum across many, many different types of systems, you're easily going to get above 250 megahertz. So we need to look at the impact of undersampling on capacity communication systems. We also never take into account processing. I think this is a real shortcoming of the theory that we've developed as communication and information theorists. We never look at complexity constraints or energy constraints on the hardware side. And I'll talk a little bit about some results at the end of this, which show that that really changes considerations when we're looking at theory as well as communication system design. And then I'm not going to talk at all about finite precision, but again, the maximum number of bits that we get is 8 to 16 bits. And that's actually one of the biggest limitations in doing multi-user detection. So there's two constraints. There's not very many practical systems that do multi-user detection, although it's making a comeback because in order to get this communication link closed at -7 dB, Qualcomm is actually proposing in the LTE standard to do multi-user detection. So one of the constraints on doing multi-user detection in practice is the precision on the A to Ds. Now, why would that constrain our ability to do multi-user detection? Isn't multi-user detection an algorithmic problem? So you could say maybe the processing is a problem because it's very complex, and that is true. But the A to D precision is also a problem. Why? Hint, near-far problem. Dynamic range, okay? So you've got a really strong signal and a really weak signal, and you want to do multi-user detection on it, okay? Well, having a really strong signal is great because you can detect it, treating the other signal as noise, and subtract it out, in theory, okay? What happens when you go through an A to D? What happens to this guy down here? Goes away, okay? Because he's outside the precision of the A to D converter. So you still have your really strong signal, but you don't have your weak signal anymore. So there's nothing to do multi-user detection on. So A to D precision and processing are the biggest limitations to implementing multi-user detection. Even though it's been around for decades, it still has not found any widespread use, certainly in handsets and very limited in base stations. Okay, so last question on this slide. What are some other asymptotic regimes that, that we look at in theory that aren't really realistic in practice? So cost is one too, right? I mean, if you go to build a system, a lot of the things that we assume with designing these really sophisticated communication systems assume size and cost is not a factor, whereas it is in practice. So I won't dwell on this anymore, but think about it because a lot of our results really don't take into account practical constraints, which is a good thing. Again, I don't think that we should look at size and cost when we do fundamental theory. Why not? What's that?
Technology dependent?
Yeah, that changes with technology. I mean, we're down to 25 nanometer chips, okay? So, whereas when Shannon was building his stuff, there weren't even transistors, okay, or designed to his theory. So, you don't want your theory to be constrained by the evolution of technology. And cost and size are certainly things that tend to be hard to, they are not barriers in terms of technology evolution. Whereas something like feedback or energy is far more fundamental. Okay? All right. So now I'm going to talk again. I only have one slide on this, and it probably doesn't even have the most recent results, but I wanted to briefly mention the work that's been done on finite block length, both channel code, source codes, and source and channel coding. So if you look at where information theory started and evolved from Shannon's work over the next several decades, it was really looking at, from a channel coding perspective, if you fix the rate, how do you drive the error probability to 0? And so Gallagher's book and even Shannon's early work, as well as Chizar, Corner, and Martin, talked about having an epsilon, that's the probability of error, as a function of the rate that you're trying to send over the channel. And of course, if the rate is below capacity, then that probability of error will go to 0. Similarly, with lossless source coding, there was also a notion of the distortion associated with the source code as a function of rate. And if the rate was above the entropy, then that distortion would go to 0. With lossless source coding, you don't get an epsilon that goes to 0. You get an epsilon that's a function of the rate and some other parameters. And finally, with joint source and channel coding, this goes back to Chizar's book, the epsilon is a function of both the rate and the distortion. So the key to all this is that this early work was fixing the rate R and looking at the probability of error as a function of things like block length. Now, the new work, which is based on this notion of dispersion, and as I said, there's several teams working on this. Two members are here. Victoria Christina, who's been working a lot on source coding, as well as joint source and channel coding, and Amir Ingber, who's done work in similar areas. So all I want to say about this is that the fundamental change in looking at finite block length codes is you can't drive the epsilon to 0 anymore, right? I mean, that's a fundamental premise. You need infinitely long codes to drive the error probability to 0. So instead what they did is they turned the problem around and said, let's fix the epsilon and figure out what rates we can get for those fixed epsilons. And these are, again, based on notions of channel dispersion. Actually, roots of this go all the way back to Strassen's work, and for both sorts and channel dispersion. And again, here are some formulas that I took from the most recent literature, and this is evolving. One other extremely important point about this finite block length work, which we alluded to earlier, which is that, again, from the Cesar and Corner book and also his earlier papers, he showed that separation is optimal because this error exponent basically puts all the distortion into the source. And so you compress the source down to the channel capacity rate, and then you send over the channel at that rate with no distortion. Whereas this new work on finite block length shows that separation is not optimal. That now that you have a finite block length channel code and a finite block length source code, they should be designed together, not separately. And so the other thing I wanted to share with you is I mentioned that we've had several workshops about grand challenges for the center. And one of them we just had a couple weeks ago at the Con Theory workshop in Maui. And there were Mai Tais, so of course the discussion got very interesting. But one of the, I think, most interesting and heated exchanges was between Sergio Verdugo and Ronaldo Valenzuela about the value of these finite block length codes. So Ronaldo, who actually his group was responsible for all of the original MIMO development at Bell Labs, started out the discussion a bit skeptical. And he said, well, you know, in practice, we have everything we need. So in practice, from the perspective of the cellular industry, Shannon's bounds using these error exponents are within half a dB for reasonably sized packet lengths, 30 bits or more, and that's what we use in practice for additive white Gaussian channels and reasonable BERs. So why do we even need to look at these finite block length coding results? Okay, so the response was, and I'd love to hear if people have other opinions on this, okay, but if you move away from the AWGN channel, in particular if you start looking at practical fading models, there's very little work. Only the bounds that Safian computed were only for additive white Gaussian noise channels, which aren't practical for many systems. Moreover, the computational effort that is needed to compute these bounds based on Shannon's bounds is very large. So that indicates a need for accurate approximations such as the ones that I showed on the previous page. And that was the consensus of all the people that this is very valuable. Maybe not so much for an additive white Gaussian noise channel because computational complexity can be tamed with enough computational power, but for the large range of channels that we're looking at, we need better ways to approximate how codes, source codes and channel codes, perform under finite block length constraints. Okay? So that's all I'm going to say about finite block length, unless there's any questions or comments. Okay, so let me move on to, I was going to preface this section by saying I haven't worked in this area, so I know very little about it, but that never stops professors from talking about things. So, but the next few topics I do know something more about, because these are works that mostly have been done within my research group. So let's talk a little bit about MIMO systems. MIMO systems are extremely powerful. They're used in every modern wireless communication system. And the reason is because having multiple antennas, so MIMO stands for multiple input, multiple output. It means you have multiple antennas at the transmitter and the receiver. And you can use those multiple antennas in different ways. So by doing a singular value decomposition on the MIMO channel, you basically get multiple signaling dimensions. These are also referred to as degrees of freedom. So if you take the matrix of channel gains and you decompose it along the singular value decomposition, the number of channels that you have is the rank of that matrix, and the gain on the channels is the singular value associated with that particular dimension. So not all of the channels have the same gain, and thus some of these spatial channels can be error prone. So in particular, if this channel is associated with the smallest singular value of that matrix decomposition, it will have a much lower signal-to-noise ratio than the channel at the top. Okay? So I can get high data rates by doing this decomposition, because instead of just having a single stream of data from the transmitter to receiver, now I have 3 streams of data. Okay? But they're error prone. So alternatively, I can do diversity combining at both the transmit and receive side. The diversity gain is the product of the number of transmit and receive antennas. So the more antennas you have, the more diversity gain you get. And so that leads to a very robust system, very low probability of error. But I give up the spatial diversity, I give up the spatial multiplexing, I give up the additional data rate. So using multiple antennas was known for a long time, but characterizing this diversity multiplexing trade-off wasn't done until Zhang and Say's beautiful paper in 2002, which looked at asymptotic limits of this diversity multiplexing trade-off. And the way they defined diversity and multiplexing is they said, okay, if you look at the rate as a function of SNR and divide by the log of the SNR, that's the pre-log value. So that's basically giving you how many spatial dimensions you have. Okay, so this little r is the spatial multiplexing gain. R is equal to the rate divided by log SNR. So if you looked at the capacity formula, that would tell you how many spatial streams you have. In the limit of high SNR, in that limit, all these channels are equal, right? Because it doesn't matter if one has a low singular value if SNR is infinite. Okay? And the diversity gain is basically how much you reduce the probability of error by doing this diversity combining. So they define that as the log of the probability of error. You can think of it as the change in slope of the probability of error due to diversity. So they define this as the log of the probability of error divided by the log of the SNR. And their result, which is so simple, it's truly beautiful, is that the optimal diversity, the maximal diversity gain that you get as a function of the number of spatial multiplexing streams you have, is the number of transmit antennas minus R times the number of receive antennas minus R. So it's this piecewise plot here. If you're using all of your antennas for diversity, then you get the product of NT times NR. If you're using all of your antennas, you can't read this. That's not intentional, but it's helpful right now. So if you're using all of your antennas for spatial multiplexing, what's the maximum spatial multiplexing gain you can get? Hint, it's the rank of the matrix associated with this MIMO channel. And what is the maximum value that the rank of that matrix can have? Min of NT and R. So this is min NT and R, and you see that it's piecewise linear here. Okay? So where is the asymptopia in this result? SNR. So there are these two limits. Okay? SNR is going to infinity. So what if we don't look at infinite SNR? What if we look at something else? Okay, so the myth of this diversity multiplexing trade-off is that you should use some antennas for multiplexing and some for diversity. And I'm going to return to that in the joint source and channel coding context shortly, but for now, that is the conclusion from this plot, that you can operate anywhere on this plot and you'll make a decision as to how many dimensions you want to use for multiplexing and how many for diversity. Okay? But that's in high SNR. So if you look at practical systems, and this is based on a paper written by Lozano and Jindal, former Stanford students a few years ago, it turns out that what they show is that you should use all of the spatial dimensions for either diversity or for multiplexing, but not both. So in particular, these are two plots taken from their paper. And what matters a lot is whether you use hybrid ARQ or not. Okay, ARQ all the time. Hybrid ARQ just means you're trading off coding and ARQ. So you can just think of that as ARQ, one-bit feedback, whether you made a mistake or not. Okay, so what they show is that, in this case, there's no ARQ. Okay? And what they show is without ARQ, if you want to maximize your rate as a function of SNR, finite SNR, you should always use all of your dimensions for transmit diversity. Okay? You shouldn't use your dimensions for spatial multiplexing. Why do you think that is in the absence of ARQ? And by the way, you get the opposite result with ARQ, assuming some outage, because it's not infinite SNR, so you make mistakes. So with ARQ, you use all of your dimensions for spatial multiplexing and none for transmit diversity. You do much worse if you bring in diversity. Okay, so why is that? Why does ARQ make all the difference between how you use these dimensions? Yeah, Reza.
Because feedback gives you information about the channel, and then for spatial multiplexing, you need to.
No, this is assuming perfect channel knowledge, okay? Because you couldn't do spatial multiplexing without it. So assume you know the channel perfectly. I'm not looking at feedback in general. I'm just saying the difference under perfect channel information between using ARQ and not using ARQ. Sorry, the other way around. Not using ARQ or using ARQ. Any idea? So let's go back to the principle of diversity versus multiplexing. If I use all my antennas for diversity, what do I gain? That's the 2 slides ago.
Low probability?
Robustness, low probability of error. Why would it be important to have a low probability of error, because I'm using all my antennas for diversity, in the absence of ARQ?
It's hard to drive the outage down.
I can't recover from errors, right? I can't retransmit. So if I have a fixed outage, I have to achieve that on the forward transmission. There's no other opportunity to send that data. So without this stupid little 1 bit of feedback, it completely changes how I should design my system, because robustness becomes the most important characteristic. And that's why you use all your antennas for diversity. With this 1 bit of feedback, everything changes. Okay? Because now, okay, the system's not quite as robust. I'm still operating at decent SNRs. Remember, minus 7 dB, they're closing links in LTE. Okay, so 0 isn't even a bad SNR anymore. So I'm only making mistakes once in a while. I'm allowing myself 1% outage, so whenever I make a mistake, I just retransmit. And by doing that, spatial multiplexing is the best thing. And by the way, another conclusion of their paper, which is done in practice, is that you adapt the modulation encoding to the channel SNR. So when you're doing spatial multiplexing, you don't use the same modulation encoding on every one of your spatial streams. Why not? Does each spatial stream have the same SNR? No. And what does Shannon tell you when you have different channels with different SNRs? You adapt the rate encoding. Okay? So you adapt modulation encoding to the channel SNR. And so really what they're saying is in practical systems with a single bit of ARQ, you use all your dimensions for multiplexing, spatial multiplexing. You don't need diversity anymore. Very surprising conclusion, very different from the one under infinite SNR. So there are results actually bringing ARQ into the diversity multiplexing trade-off. So now it's called the diversity multiplexing ARQ trade-off. This is done for single links, and it's also been done for multi-hop systems. And the idea is that ARQ is really a form of time diversity, because you're just resending the same information later in time. And so it's a form of diversity, and therefore it's going to push up the diversity multiplexing trade-off depending on the ARQ window. So L equal to 4 means that you wait, you do up to 4 retransmissions. If L is equal to 1, there's no retransmission. And so this is the gain you get, diversity gain you get from ARQ. So you can formalize that, but this is still an infinite SNR result. So it's not going to tell you what the previous page where you're looking at finite SNR does. Okay, so now I want to talk a little bit about source and channel coding under this diversity multiplexing trade-off. My students, Stanford students, have seen this before. I apologize, but that's okay. You can't answer the questions. How's this? Okay, so now I'm trying to send a source, say it's an image, over this multiple antenna system. And again, the question is, I can use my antennas for multiplexing or diversity. In the Jindal-Lozano results, they were just looking at rate. So they were just looking at throughput, assuming either they retransmitted or they didn't. Now, I'm looking at trying to send a source over the channel. And again, same thing. I can use my antennas for multiplexing, but now some of these links are going to be error prone. So what happens is, if I use my antennas for multiplexing, I have this very high resolution image. I don't need to compress it very much, or maybe I don't need to compress it at all. By the way, that's what a lot of these HDTV wireless systems are doing, is they're trying not to compress because you have this huge screen TV and you don't want to mess up the image. So you send the image not compressed or slightly compressed over this high rate channel, but the channel's error prone, so you get some errors in the image, okay? Or you can go the opposite extreme and use all your antennas for diversity. Now I have a low rate channel, or at least the rate of this channel is 1/3 the rate of the other channel, so I have to compress the image by a factor of 3, so it gets fuzzy, but it's very robust, so there are no errors. I get a fuzzy image with no errors. And the question is, okay, so how should I use my antennas? And, okay, so how should I use my antennas? Would you rather have this image or this image? Okay, how many people say they would rather have this image? Raise your hand. Okay, and how many people would rather have this image? Raise your hand. Okay, so bottom line is that it depends on what you're looking at the image on, right? If this is your cell phone, maybe that's fine. But if this is the HDTV that you paid, $5,000 to get HDTV resolution, and you're getting something that only looks good on a cell phone screen, then you're going to take it back to the store, right? Now, okay, so that would say if I'm buying a $5,000 HDTV screen, this is the image I want. Is this the image you want if you paid $5,000 for your HDTV? Well, only if those white things are so infrequent that you don't even notice them, okay? Now, if they're frequent, how do you design your HDTV? Okay, so suppose if this is the choice between this with these white things coming up every couple seconds, or even every tens of seconds, or this fuzzy image, how do I answer this question? How should the antennas be used? Where's the entrepreneur in the audience?
Partly, you should combine them. Not all of them. You should not use all of them to do something amazing.
He's clearly not an entrepreneur. Okay, so you're saying it should be somewhere between these two. I paid $5,000 for this screen, okay? You're giving the startup company an unacceptable choice. You need more antennas, right? You need to have a better trade-off so that you can get this with some antennas and use the other antennas for robustness to get rid of the white ones, okay? So basically, you have the wrong diversity multiplexing trade-off because you don't have enough antennas to meet the requirements, the end-to-end metric of this application, because for a $5,000 HDTV, you need good precision and good robustness, so you need more antennas. Okay? Now, we actually...
You can also use joint source channel coding.
I'm sorry?
You can also use joint source.
Oh, thank you very much, and you didn't even see my slides. Okay, so this is based on some work that I did with my former student Tim Holliday a while ago. Yes, you can use joint source and channel coding. So the trade-off now when you're doing source and channel coding is if you increase the rate of the source coder, then you decrease the source distortion, but then you have a higher rate, so you need to use your space-time code with more spatial dimensions, which means that you have less diversity. And then you're going to get more errors in the channel decoder and maybe a higher total distortion. So the question in a practical joint source and channel code design, away from the asymptopia of infinite SNR, is how should you design this source and channel code to minimize the total end-to-end distortion, Okay, so you need to do a joint design, and this is again based on some work we did some time ago, and I didn't put the reference here, but I can if people are interested. And basically, it tells you what you expect. That basically, so the EB over N0 here is all normalized, where 1 is the largest and 0.1 is the smallest. And what happens when you have a quote-unquote high SNR, this curve, how am I using my antennas? I'm using them all for multiplexing. This is an 8x8 system, okay? So I'm using all my antennas for multiplexing to get the minimum distortion. But all these other SNRs, there's a local minimum, which tells me, for example, if I take the red one, which is 0.25 SNR, I should use half my antennas for multiplexing and half for diversity. So the lower the SNR, the more diversity I need, and the more antennas I use for diversity, and the higher the SNR, the more I don't need to worry about robustness, so I use my antennas for spatial multiplexing. Okay, so any questions about the MIMO systems or diversity multiplexing trade-offs before I move to the next topic, which is relay? Yeah?
I just have a quick question. I know this was just an example, but I mean, suppose you are sending like an HD stream, right? I mean, the frames are so large, then it just seems like, I mean, the data frames are so large that there would be very small benefits from using joint source channel coding because your block lengths are big enough where you practically live in asymptopia, right?
So that could very well be, and the work that I showed was not looking at HDTV or large block
I know
lengths.
this is just an example.
But I think that's a good point. I mean, so
because
the
it
thing.
seems like a lot of the things where we need really high resolution, I mean, it is something like streaming video or whatever, where the frames would be bigger.
Not necessarily. Well, I mean, pictures too, right? If you're sending a picture, it doesn't have to be a video. But that's an excellent question.
I mean, because
There
10,000
is a-
bits is essentially, asymptopia as far as
From the
total
source
goes.
side, but you're not sending a 10,000 bit channel code typically. So you could say that on the source side, and by the way, the codes that we use for streaming video, like MPEG and JPEG for pictures, are not very good codes from an asymptotic perspective anyway. So what you could say there is, okay, what happens if you're living in asymptopia on the source code side, but the channel is going to introduce distortion because you don't have such long codes on the channel coding side? Or again, should you be compressing that HDTV signal more so that you can either do more robust channel coding or have longer block length codes? So I think your question is, one, it doesn't violate what I said on this slide. How should the antennas be used? It depends on the end-to-end metric. The end-to-end metric is always going to be total distortion. But what you're saying really is that you're living here, where your source coder is such that you really don't have a lot of distortion on the source coding side. And then you have to say, well, okay, in that case, probably you would want to use your antennas for spatial multiplexing because you need as much rate as possible. But again, if there aren't enough antennas, you may say, no, I need a different type of source code. Right, and there's certainly a lot of work on variable rate source coding or having different possible source codes depending on what the channel rate is, right? So, in practice, it's important to look at the practical scheme that you're using and saying which asymptopia does it live in or live out of, and then study the problem in that regime. Were there other comments on this? I thought it. Yeah.
Just on Tom's question.
Can you?
There's at least one company that is based on the fact that you do want to use joint source coding in this case. And one of the reasons is that your model for the source is not mirrorless and is not something that you can easily capture with a good source code. So we can really benefit from doing this together. So if the channel becomes bad for a certain part, then you only lose a certain part of the image, which is usually totally.
Another important issue that brings up, I think, is that the metrics we use for images and video don't well capture the human experience, whereas the joint source and channel coding can capture it better. So if you look at the total distortion, say, metric, which is usually 1 over the PSNR or something like that, it's not really capturing what somebody sees, whereas a joint source and channel code can do that. It says, okay, the channel's bad for a while, so we want to compensate for that. When the channel's bad for a while, that doesn't always come up in PS and R, right? Because it's just a short segment of time. A lot of these metrics are averaging over infinite time. It's not capturing the fact that I want my picture to be good every millisecond, right? So I think that also comes into the joint source and channel coding, that if you see that, and in the same way that the channel can be bad for a while, a variable rate source can have a very high rate at some point. And if the very high source rate coincides with a very low channel rate, then again, you want to do something in the joint, so at least exchange the information about, okay, this is the channel rate, this is the source rate, how do we compromise? Do we put distortion in both the channel and the source? Do we put it on the source? Do we put it on the channel? So I think I've been a big fan of joint source and channel coding for a long time because I think there's a lot of untapped research to be done there. Shannon's separation theorem did a disservice in a sense because most people said, oh, it's optimal to do it separately, and the source coding people went off in one direction and the channel coding people went off in another direction. Whereas outside of asymptopia, we already know separation isn't optimal, but all of these practical type systems also have other considerations that aren't captured in Shannon theory. Okay, any other questions or comments before I move on to relay? Okay, so why do we do relaying in networks? So there's kind of two types of wireless networks. There's cellular type infrastructure where you have a base station or an access point and a Wi-Fi network talking to lines or phones. But in multi-hop networks, you typically use a relay to help forward information to the final destination. And that's in part because you could do single hop transmission from the source to, oh, the arrows are going in the wrong direction, sorry. From the source to the destination, but that may create too much power. If you look at a typical path loss model for a wireless channel, you minimize transmit power by using an intermediate relay. So the transmit power of a multi-hop network is minimized by using an intermediate relay. So there's many reasons to use a relay. Decode and forward, so there's many, and there's also different ways of doing relay. So decode and forward is pretty much the most common thing that's used in practice. What you do is that the relay receives the information from the source, decodes it, and then forwards it on to the final destination. So this removes noise at the expense of complexity and delay of the relay, because the relay has to decode. You can also use the relay just to do amplifying forward. So then the relay is going to amplify the received packets, but that also amplifies the noise. So this doesn't work so well for low SNR. And compress and forward, the relay receives the information from the source, compresses it, and sends the compressed version to the destination. Now, if the relay does compression, is there distortion introduced? Of course, because if I'm compressing the data, then I'm going to introduce some distortion unless it's lossless, which if you could do lossy compression at the relay, you might as well do it at the source. So typically with compressing forward, the relay is compressing the packet, introducing distortion, and why would you want to do that? Well, you do it when the source to the relay link is good. So the relay can get the source data perfectly, but the link from the relay to the destination is not so good. So if the rate on that link is lower than the rate between the source and the relay, then you have to compress the data because you can't transmit it at channel capacity. Okay, so these are the three techniques that are commonly used in the literature, and people look at it from a capacity perspective. Now, the capacity of the relay channel is unknown. It's been an open problem for decades. We have upper and lower bounds on the capacity of the relay channel. We have results that show that these are optimal in certain situations, but we don't know the capacity of the relay channel. Okay, so, and relaying is just one form of cooperation. So if you think about having a bunch of nodes and they're all trying to communicate with each other, you can do relaying, but you can do other things when you have multiple sources and multiple destinations. For example, you can do virtual MIMO. So we already talked about why MIMO is so good. So if you've got nodes that are close together, they can talk to each other and form a virtual MIMO transmitter. These guys could form a virtual MIMO relay, and these guys can form a virtual MIMO receiver. You can also have generalized relaying, which I'll talk about shortly. If you have multiple sources, this guy in the middle can help to transmit that information to multiple destinations. You can do things iteratively. So if this guy is broadcasting and these three guys receive some version of what was broadcast, they can iterate between them like is done in message passing and LDPC decoding to decode the final message. And these are just a few examples. So there's many, many different ways to do cooperation in wireless networks. Since we don't even have the capacity of the simple relay channel, we don't know the capacity of these techniques either, but we can compare them, and that's often what we do. In addition to the capacity analysis of these techniques, there's many theoretical and practical issues, like overhead. If I'm going to do virtual MIMO, how much overhead is associated with the nodes that are communicating with each other? Who should group with who? What if the channel's changing? Many of these results assume full duplex relays, which actually there's been some nice research recently on doing full duplex, but most practical systems are half duplex. Most of these results assume all these nodes are synchronized, and often they don't have GPS and so forth. So, so there's many interesting research open still in cooperation in wireless networks. But I want to give some advice, which is, if there's a problem that's been open for decades with people really smart, like Cover and Elgamal working on it, and they haven't solved it, you probably don't want to do research in that area, okay? So what do you do if you think relaying is cool and it's a topic you want to work on? You don't want to give up. So the best thing to do in research, if there's a really hard problem that smart people have worked on for a long time and gotten nowhere, change the problem, okay? So this is what we did recently. This was work by my former postdoc, Yvonne Mark, and I, and Miro Bedard, which was, okay, we can't solve the relay problem if we have a single transmitter, a relay, and a receiver. So let's add another communicating pair. So we added a second transmitter and a second receiver. Okay, so now, the reason this fundamentally changes the problem is that in the first case, the only role the relay has is to help forward information from transmitter 1 to receiver 1. Okay? But now the relay has two transmit-receiver pairs that it's trying to help. Of course, it can still forward all or part of the messages from the two different users to their respective receivers, and again, there's much room for innovation there. But the way that this fundamentally changes the problem is that now you can also have the relay forward interference. Now, why would I want to forward interference? Isn't interference a bad thing? Is interference a bad thing?
Not in the high interference regime.
High interference regime when you can subtract it out, okay? So why would you want the relay to forward interference? Well, you're going to get interference. So transmitter 1 is going to interfere with receiver 2 no matter what. But if the connection between transmitter 1 and receiver 2 is weak, by having the relay amplify that interference at receiver 2, now you push it into the strong interference regime where you can subtract it out, okay? So that's the idea of forwarding interference. And we still don't have the capacity of this channel, because if we did, then we'd have the capacity of the relay channel, because we could just make this channel gain 0 or something like that. So we know we're not going to solve it, but we do have some interesting results on forwarding the interference in the message. And in particular, what we showed is that if you treat interference as noise, so basically the relay doesn't play a role here, you get a rate region of the two pairs, R1 and R2, of this box. If you forward the message, then you get a better rate. And if you forward the message and the interference, then you do even better, okay? So this is the notion that, again, by changing the problem, adding a new dimension where we can forward interference, we can do better than all the existing techniques. Moreover, actually, we can achieve capacity in a very special network. So in this network, it's a layered network where we have a source, a pair of relays here, a pair of relays here, and then the final destination. And what we showed is that if these powers, PS, P1, P2, P3, P4, are going asymptotically large, so that's the asymptopia here, then this amplifying forward achieves the map cut set upper bound. So we know for this network, we can't possibly do better in terms of rate than the cut set across the destination. That's in red here, and this amplifying forward does achieve that upper bound. Okay, so what asymptopia is going on here? Is this highest in our regime? What does highest in our regime even mean in this context? Because there's different SNRs at every node, right? So what happens is that, okay, suppose I have a very large channel gain here, okay? Then regardless of what the power is here, this guy will have high SNR. But then, when he amplifies to this guy, what happens? The noise is also amplified. So if I have a high channel gain here, he won't have a high SNR because he gets the noise amplified from this guy, okay? So high SNR, you have to be careful in a multi-hop network what it means. The only way you get high SNR is not by looking at the channel gains. It doesn't matter what the channel gains are because the noise is getting amplified on every hop. What matters is the powers, okay? So as long as the power of the signal that you're sending in each hop is large, the amplified noise power is going to go to 0. And that's the asymptopia that we're living in with this result. Okay?
Question?
Yeah.
So can you apply this result to the simple diamond relay network?
Yeah, we have in that paper, there's also an application to the diamond network. We don't quite hit the upper bound in the diamond network.
Can you generalize the number of relays?
I think so, but I don't remember off the top of my head. I think that as long as you have this very regular network and you have the powers approaching infinity for every hop, I think you get the same result, but I'm not 100% sure about that. Okay, so, and then there's the interference alignment, which we talked about before, where we say, okay, interference alignment says that if you do, if you orthogonalize users in an interference network, then basically you have to take the total degrees of freedom and divide by the number of users. That's the maximum number of non-interfering links you can get. But through interference alignment, which is basically you align all the interference that a particular node sees in one dimension, and then say it's the time dimension. So half the time, you're only getting interference, but all that interference is aligned on top of each other, and then the other half the time is interference-free. And that means basically everyone gets half the cake. So rather than having to divide the total number of degrees of freedom by n, you just divide by 2. The problem, so that's great, and I like cake, so getting half the cake is a good thing. But at finite SNRs, we don't get half the cake. We're back to the orthogonalization. And there's been some interesting recent research about what happens to interference alignment in the finite SNR regime. But another thing that came out of this workshop that we had in Maui was that in industry, they're very skeptical of interference alignment because they don't see these gains at the SNRs that practical systems actually operate at. Okay, so going to this whole topic of relaying and cooperation, backing off from infinite SNR, what can we conclude? Okay, so there's this high SNR myth, which is that decoding forward is exactly the same as amplifying forward at high SNR. Because at high SNR, there's very little noise anyway, and so just amplifying the signal is almost equivalent to decoding it and forwarding. Or another way to say that is that the impact of amplifying the noise diminishes at high SNR. But that's really only a single hop, a single link result. If you have multiple hops, every hop you're amplifying the noise. So even if you only amplify the noise a little bit on one hop, as you keep hopping, you keep amplifying the noise. So you have to be careful about even defining high SNR in a multi-hop network. So again, where did this myth come from? Where there were results that said amplifying forward achieves the full degrees of freedom in a MIMO system, but again, just a single hop. And then this was from that same, an earlier result, sorry, this is the 12 paper, is amplifying forward is within a constant gap from the capacity upper bound as the received power increases for a large set of networks. So that's where it comes from, but in reality, if you look at practical SNRs, as you would see in practical systems, amplifying forward is highly suboptimal. Amplifying the noise is very detrimental to your overall performance. And again, you have to be careful about how you define high SNR. So you need high SNR per node to make amplifying forward near optimal, because you have to make sure that when you do amplifying forward at that node, the noise is small so that the amplification doesn't have that much effect. And again, there was a paper that appeared last year showing that amplifying forward has an unbounded gap from capacity in the high channel gain regime. This is for the diamond network, okay? And again, the reason why this result seems so contradictory to the ones that say amplifying forward is near optimal is because they were looking at the high channel gain regime. So again, high channel gain just means that on the first hop, you get the signal well, but the noise gets amplified on the next hop with the high channel gain, and therefore you're not in the high SNR regime anymore. Okay, so really, the relay strategy you use, and this goes back to the point I made in the first slide about relaying, is that in practice, it depends on the worst link. So it's SNR dependent. And I'll see if you were paying attention. And again, the arrows are going the wrong way, so just pretend they're flipped. Okay? So when should I use amplify and forward? For this simple relay channel. When is that optimal? There's only 3 links here. So what should the SNR be on each link?
I think we should cut off this free lunches for this too.
Or my talk should go before lunch, so they're paying more attention. Okay, all right, let's take a vote. That's always a good democratic way to solve things, unless you're in Egypt, Syria. So, okay, so how many people think that this is, this amplifying forward is optimal in highest SNR regime? Raise your hand. Okay, so amplifying forward, highest SNR at every node. Okay, raise your hands high. Come on, don't be shy. I'm not going to shoot people for being wrong, and I won't hold
I was fired
these
already,
hostage.
right?
You can still go to dinner, even if you're wrong. Okay, and okay, how many people think in medium SNR, low to medium SNR regime, that amplifying forward is optimal? Nobody. Good. No, nobody, because you're amplifying the noise. You're fired too. All right. Okay, fine. So when is decoded forward optimal? Okay. Highest SNR regime, I mean, it's still going to be optimal. That's the best thing that we can do. But the point with decoded forward is that if this link, okay, I'll do a vote here. Decoded forward is optimal either when this link is high SNR or low SNR. How many people say decoded forward is optimal when this link is low SNR? How many people think decoded forward is optimal when this link is high SNR? Okay, so someone who hasn't spoken yet. You, why? Why?
Because you're not losing anything on the channel. I mean, if the channel is low SNR, you should really compress it.
Absolutely. I can't get the message across here if it's low SNR, right? So I need to compress or just amplifying forward. I cannot decode. In order to decode at the relay, I need to have a rate on this link commensurate with the rate that the source is sending. Okay, so I need a high SNR. And compressing forward is optimal when, I already said it, when basically this link is good, but this link is bad. So that I can decode at the relay, but then I have to compress it in order to get it across this link. Okay. And decoded forward is used in practice. I don't know of a single practical multi-hop network that uses anything other than decoded forward, because you don't want to make mistakes, yeah? Do you know of one?
I think a lot of these, I mean, maybe it doesn't fit exactly in the context of a relay channel like that, but a lot of satellite relays use bent pipe, which is just amplified.
Yeah, that could be. I'm thinking more of terrestrial networks here, or large numbers of hops, but yeah, that's certainly an example. Okay. All right, so now let's talk about feedback. Capacity under feedback is largely unknown, okay? So we don't know capacity of channels with memory under any type of feedback in general, except very special cases. When the rate of the feedback channel is finite or there's noisy feedback, there's very few results. And we certainly don't know much about using feedback with multi-user channels and multi-hop networks. Did you have a comment?
Well,
okay. But as I've already pointed out, ARQ is ubiquitous in practice, and it works well when the feedback link is finite and noisy, because you're only sending a bit, and even if there's noise, you can code it so that you're extremely unlikely to make an error on the ARQ. ARQ not only helps in driving the probability of error down, it also reduces end-to-end delay, because if you make an error on a multi-hop network on a single link, rather than waiting to get the fact that you made an error through TCP/IP at the end of the whole multi-hop train, you know just from the link that you made an error and you can do retransmission. So given that we have almost no results for feedback, and all the feedback capacity analysis that we've looked at are things like no noise, infinite rate, why is there such a disconnect between theory and practice? We use 1-bit ARQ in practice. And we don't even look at that in theory. In theory, we go the other direction. Infinite delay, infinite rate, no noise. Any idea why there's this big disconnect? So I don't know why. I think a lot of it stems from the fact that it's been so hard to get any kind of results under feedback. So there's very, very limited results, and so we haven't even, usually what happens is you take kind of a very general setup and solve it and get insights, and then you specialize. We still don't have the general results, so nobody's bothered to look at, okay, finite rate, noise, etc. until recently. So, okay, and I think the other reason is due to Shannon, because he said feedback doesn't increase capacity of discrete memoryless channels, of course, with that caveat. But in the same way that separation is optimal, is all that people remember from the separation theorem, even though it applied to memoryless channels in very specific setups, the fact that feedback doesn't increase capacity, Shannon says, means, well, then what's the point in looking at feedback? I'm just going to spend many years studying the problem only to get a result which says all that work was useless because you shouldn't use feedback. Okay, so it doesn't increase capacity of a memoryless channel, and the reason is if the channel's memoryless, there's no information you get from the feedback that can help you increase your rate. Okay, the channel is memoryless, so transmitting a symbol on this channel is completely independent from transmitting the symbol on the next channel, so there's no use from feedback. Okay, but it's not useless for something other than capacity. In particular, it can drive the error probability down much faster. So I already talked about the Gallagher error exponents, and these came out of Shannon's work as well. The error exponents go down exponentially. With the Shawlett-Kailas scheme, you're using a very simple linear recursive scheme in the feedback, it's capacity achieving, but it drives the error probability down double exponentially. Okay? So this is helpful, again, if you're looking at finite delay systems with non-zero errors, you can get a much lower error given a particular delay by using feedback. Okay? And that's been known for a while as well, going all the way back to Pinsker and Gallagher's work. So this is the error exponent with no feedback. Okay, so there's exponential decay. With Gallagher and Pinsker's work, they said if you have perfect feedback, so infinite rate, no noise on the feedback link, you get this exponentially decreasing. So it's e to the e of O of n. So it's going much, much faster. Okay, so this is the probability of error that you get with Gallagher's error exponent. This is the Kailas-Shockley scheme, Kailas-Shawlett scheme. And then this is the rate that you get with the feedback. But if you have noise on the feedback, this is a result by Kim and Lapidot, and I think Wiseman too. As soon as you add noise, feedback doesn't help you at all. Noise on the feedback link. Okay? So this idea of needing no noise on the feedback link is really important in terms of driving your probability down. And then there was also work by Fayansky and Verdue and Poor, I believe, that noiseless feedback can reduce the minimum energy per bit. Okay? So what we're seeing here is that maybe it doesn't help with capacity, but it can certainly help with driving the error exponents down and reducing energy consumption. So we've been doing some recent work on that. This is with my student Reza, where now what we're looking at is rate-limited feedback. So this is different than the Gallagher-Pinsker result because they assumed infinite feedback. And so the idea is that, you know, you have some message, standard setup, you decode it, and then you feed we're trying to drive the error probability down as low as possible through this feedback scheme. And so we're choosing the feed forward and the feedback functions to do that. And what we found is that if the feedback rate is less than the feed forward rate, the feedback doesn't help. Okay? Or it doesn't change this linear error exponent. So if the feedback rate is less than R, the error exponent is finite. It's higher than no feedback, but it doesn't go above the exponential. So it's still got an exponential decay. If it's bigger, if the feedback rate is bigger than R, you get the same double exponential error probability that Kailath and Chalmers found. And what's more important is that suppose you have a huge feedback rate, okay, L times the feed forward rate. You get an exponential decay that's L-fold of the original error exponent. Okay, so basically you're driving the probability of error to zero very, very fast. And this is interesting in context, obviously, where you have a much higher feedback rate than feed forward rate. Can you give me some examples of where that might be the case?
Cell phone, ultimately.
Well, it's unfortunately not L, and in fact in LTE it's factor of 2. The uplink is about half the downlink. So we can do better, but it's not like 100 times. So where might it be 100 times or 10 times faster? The reverse direction.
Sensors that only transmit loop data.
Sensors that are getting data for, yeah, okay, so a sensor network where you have a lot of constraints on the, receive constraints. When you have receive constraints, but remember the receiver on the forward link is also the transmitter on the reverse link. So if you have a sensor network, how are you going to get 10 times the capacity from the sensor back to the central processing station? So maybe for certain types of sensor networks. It turns out actually that where you start to see this, and this is something that came out of being part of the center, is in biological systems. So it turns out that in the visual systems, that the feedback of a visual system, and this was talking to Jack Gallant, is much, much larger than the forward path. So in fact, this might tell us something about the way systems outside engineered systems work. Why is it that certain types of biological systems maybe need very little information coming in to get results? It's because maybe there's a big feedback path. So I was very surprised to hear him say that, but apparently that's what his research and others show. So this may not apply to any engineered communication system we know, because it's unusual that you can get much higher rate going in one direction versus the other, because the complexity is roughly the same to transmit and receive. But in other types of systems outside of the ones we know, that might be the case.
So would you give some intuition why would you ever want to send at a higher rate than what you're receiving?
Because you have a much higher capacity on the backward link. Okay,
What
so
information, what feedback could you possibly give just receiving at rate R, for example? What more could you send that?
So if this rate is much higher, then based on the communication scheme that we derived, you can drive the probability there. You could just send the bit that so you receive some information, right? It's got noise, analog noise. So it has infinite rates, right? But if you compress it, the more you compress it, the less you know actually what was received. Okay, so that's one example of where the more rate you have on the feedback path, the more the transmitter knows what the receiver saw. Okay? The receiver doesn't, if the receiver knew the information, it wouldn't have to feedback at all.
So this is for analog channels.
Sure, yeah. The feedback path has, this is just a finite rate channel, okay? But the forward channel is an analog channel. There's finite rate, there's no noise on the feedback path in this one. Okay, yeah.
When you talk about the visual system, are you talking about the cortex back? I'm just wondering.
I'm trying to remember, I believe so. So I believe what Jack told me is that the cortex back has a much higher, I guess the vessels are much bigger to communicate information, even though they don't know the nature of that information. Okay. And then we also looked at feedback under energy and delay constraints, where basically now we're trying to minimize the total energy on both the forward and the feedback path to minimize the overall probability of error. And so the results on that, which are kind of interesting, is that how you divide up your power depends on the probability of error model. So if we look at an exponential error probability model, if we assume that feedback is free, which is this black line here, then we can drive the probability of error to zero very fast. But if we have to, and if we don't use feedback at all, so we use all our energy on the forward path, then we get this blue probability of error. And what happens is, if your feedback is expensive in terms of the probability of error, the energy you need to drive the probability of error is small, then you don't use the feedback path until you have enough energy where, even though it's expensive to use feedback, it's still beneficial. So you see that basically up until this point, if this is your total energy, you don't use the feedback path, but then you have enough energy to start using it, and then it can drive the error probability down. So again, these are just reinforcing, they're different results, but they mirror some of the things that were found earlier about the fact that feedback, even if it doesn't help on the capacity front, it can either drive the probability of error to zero faster, which is important for finite delay systems, or it can help you in terms of minimizing the energy that you use. Okay, so let's see. And still, we haven't even scratched the surface about, in a multi-hop network, how we should use feedback. Should we feedback what we receive? Should we feedback channel state information, knowing that that's going to be noisy and compressed in both cases? Maybe ACKs are optimal. Wouldn't it be nice if we could come up with a theoretical result that said 1-bit acknowledgements are the best way to use a small amount of feedback? We're a long way from knowing that. So exactly how to use feedback even in a point-to-point system is still a pretty open question. It's even more open in wireless networks. And I said there's interesting applications to neuroscience because when we look at, my student Lima is doing a lot of work on trying to understand how signals flow through the brain and what the encoding and decoding processes and correlations between neurons. And it seems clear from the neuroscientists that we've talked to, there's a lot of feedback in the brain. And how is it being used? What is its purpose? Is, again, very open questions. Okay, infinite sampling. So I have two more sections, and I'll wrap up in the next 5 minutes or so. So backing off from infinite sampling, again, if you look at a classical communication channel, usually when we get the analog signal, we convert it to a digital signal. And if we assume that that sampling is at the Nyquist rate, then that allows us to take all the analog communication systems and turn them into digital systems, because we haven't lost any information when we do the sampling. And that's why, even though Shannon's original paper had discrete signals and continuous signals, nobody ever looks at continuous because we just assume we sample at the Nyquist rate. So this is recent work by my student Shannon and Yameen Eldar from the Technion, is to say, well, what if we don't sample at the Nyquist rate? So what if we have one of these very wideband systems where we can't sample at the Nyquist rate? Well then, now we're introducing aliasing because we're undersampling. So then what's the optimal input signal? It's going to look different than the optimal input signal without this aliasing distortion. What's the trade-off between capacity and sample rate? Is it even monotonic? If I sample at a higher rate, do I get a higher capacity? And the answer is not always. Depends on the sampling. And then the third question is, what known sampling methods lead to the highest capacity? So these are all kind of like achievability results. But what we really want to get at, and we just got this result recently, it'll be presented at ISIT, is what is the optimal sampling mechanism? If you look at all possible sampling mechanisms, known or unknown, for a given sampling rate, what's optimal? And even defining sampling rate under those circumstances is kind of tricky. So let me tell you a little bit about what we did, and I won't say too much so that I don't steal Yuxin's glory when he presents this at ISIT, and hopefully you'll all be there. So if I just have a single filter and a sampler, so this is kind of a classical sampling mechanism. By the way, if I don't have the filter, then capacity goes to zero because I'm not filtering out the noise, so the noise ends up dominating. So this isn't an interesting problem unless I have a filter associated with the channel bandwidth. And so basically what happens if I'm undersampling the system, so Fs is less than the channel bandwidth, I get what looks like a folded SNR filtered by the filter S of F. Okay, so this looks like kind of a standard capacity formula, except that there's aliasing involved. But the one thing that you still need to do is optimize over the input distribution. And so this is how we're optimizing our power allocation of this alias channel. And it turns out that the way you optimally allocate power is to suppress aliasing. So basically, you don't put any power at the frequencies that are getting aliased in, and therefore you effectively remove aliasing through the power allocation. You remove the aliasing that you introduce by undersampling by doing optimal water filling. Okay, but the interesting thing about this is that the capacity is not monotonic in the sampling frequency. So this is for this channel, which has these different islands, if I look at the different sampling rates with this optimal capacity, I don't get it monotonic unless I get to the Nyquist rate, and then it's constant because I'm sampling at the Nyquist rate. So why do you think it's not monotonic in rate? You would think that if you sample faster, you should get a higher capacity.
Because in some cases you at least you start having when you increase you have aliasing by unfolding. Sometimes you can sample in the sub-Nyquist rate without the distort optimum. It is impossible. So.
Right. Okay. But for here, this channel I will distort when I sample at the sub-Nyquist rate. So that's not the.
But you can increase the distortion or decrease it.
Okay. But that's not the answer. So why is it non-monotonic? For this particular channel, okay? I want an answer for this channel, not a generic answer. Yes, I can answer. You cannot answer. Actually, you can. That's fine. Yeah, go ahead. Why is it not monotonic? He's the author. Okay, so.
Yeah, for example, if you sample it at a lower rate, there may be no aliasing for this channel actually. Yeah. But if you increase it a little bit more, then there may be aliasing. So you will always get a higher capacity when you don't have aliasing. But if you, sometimes you just increase it a little bit, but you have a lot of aliasing, so you lose a lot of information.
Okay. So another way to think of it, actually.
Isn't that what I said?
No, that's not what I heard. Anyway, at certain sampling rates, when you alias, this island will be aliased right on top of this one. And so you lose degrees of freedom. If you think of this as 4 separate islands, and you can send independent information over those 4 islands, that's going to have a higher capacity than when I collapse this island onto this one, and similarly here, I'll only have 2 islands. So I've reduced degrees of freedom. So that's why it's not monotonic. And what that means is that this isn't the optimal way to sample, because there should be a way to get monotonic increase. So you can do filter bank sampling, and the idea here, and this is probably the state of the art in sampling in practice, is rather than just have a single filter followed by uniform sampling, I have a bank of filters. And now I have to optimize the design of the filter bank as well as the design of the input. And so the theorem is that the capacity of this channel with the filter banks is this formula, and it looks like a MIMO system. It's got a log, determinant, I, and some other stuff. Okay, what is that other stuff? So it's similar to MIMO, but there's no combining, and it's best to explain what's going on with the picture. So here's my filter bank, and for each frequency, that turns into a MIMO system with the aliased versions at each integer multiple of the sampling frequency. And I'm not combining these, so basically the output of this branch is going to each of the outputs of the different filter banks. And that's why the formula looks like a MIMO formula, okay? Because you're really effectively turning this filter bank channel into a MIMO channel associated with every frequency. And of course, every frequency, X of F, has its alias version that is also part of the input, because that alias version is getting folded in to the frequency F, okay? So, and now I need to optimize my filter design as well as the input distribution. So basically, there's this pre-whitening that goes on. The MIMO is associated with that picture there, and I'm water filling over the singular values of the effective MIMO channel. And what I get is that the optimal thing to do, so I have M filters here. The optimal thing to do is, say M is 2, is, so in this MIMO channel, I pick the 2 branches for a particular frequency F that have the highest S and R. So this is X of F, and this is the alias version, X of F minus KFS. The other ones I get rid of, actually this should be 1, okay? And that gives me monotonic capacity in the frequency. Okay? So this filter bank sampling at least is giving me monotonicity. I'm not losing degrees of freedom through this filter bank sampling. Okay, and then a couple other quick results. Can we do any better? What if we do sampling with the modulator and a filter? So now Q of T is modulating the signal, and I have two filters, P and S. So it turns out that one branch with this modulator and two filters is the same as a bank of filters, no matter how many I have. And this is much simpler to implement. And the intuition is that with this modulator, I can move things around, shift them in time through the modulation, and that basically means it's equivalent to this. Okay? So from a practical perspective, it's much more desirable to implement something like this. And the last theorem, which is what Gibson will present at ISIT, is that this is optimal among all time-preserving, non-uniform sampling techniques at a particular rate. And again, defining the rate when you're talking about non-uniform sampling is a little bit tricky, and that's why we have to introduce this notion of time preserving. Because if you compress the time domain, then what you're doing with sampling is not clear. Yeah?
Oh, so that's the big
right. If you compress the time domain, then what does sampling actually mean, or if you extend the time domain? So that's this time preserving basically means that you're not compressing or extending the time domain. And let me wrap up in the next couple minutes. I'm going to skip this. This is the last section, and I'll do it quickly. Is bringing in notions of complexity into code design. So the idea is that usually in code design we only look at transmit power, so we look at probability of error as a function of transmit power. What if we actually bring in the processing power as well? If we bring in processing power, does it just shift the plot a little bit, or does it completely change its slope? Short answer is it completely changes its slope. In order to do this, we actually needed to come up with a fundamental model for complexity, for power consumption in circuits. And we did that using all the tools that we use in information theory. So we used network information theory to model the information flow in a circuit. We use a decentralized estimation and complexity to come up with the energy models. And basically, and circuit power models. So that told us basically the computational energy consumption of the codes. Then we used information theory to tell us what transmit power they were using. And that gave us fundamental bounds on the total power. And just to briefly tell you how this network information flow comes in a circuit you have computational nodes that are exchanging information via these on-chip interconnects. This is actually based on work by Thompson in 1980, and Elgamal himself also worked on this type of modeling. And so if you want to come up with a fundamental energy model, you look at the area occupied by the wires and the clock cycles, because that's telling you the computational power and the computational nodes. And bottom line of all this will also be presented at ISIT by my postdoc Paul Grover, who's trapped in England due to visa reasons, so otherwise it would be here. But the bottom line is, his work says stay away from capacity. Close to capacity, you need large chip area, large interconnects, many computational nodes, you need more time to do the computation, and the bottom line is that you need more power. So basically the total power here, you say, if I just look at optimizing the transmit power with LDPC codes, I'm close to the Shannon limit, but I'm far away from it if I take computational power in. And this is what we see in practice too, because the capacity approaching LDPC codes are not what's used in practice. They're regular LDPC codes which have lower computational complexity. And with that, I'm going to wrap up. So again, the purpose of this talk is not to tell you you should look at asymptotic results. They're extremely important. They provide a lot of insight. And sublime delight to researchers, okay? So it's a lot of fun to work in asymptopia because you can get closed-form results and insights. The caution is to make sure those insights make sense for the types of problems that you're looking at. So for some problems, you need to back off from infinity to gain insight and fundamental bounds. To do that, sometimes we need to move away from the traditional mathematical tools that we've used, and we have to come up with new ways of applying these traditional tools. And again, there's very interesting problems in backing away from infinity, not only in communication systems, but in finance, biology, neuroscience, and many of the other topics associated with the center. So with that, I'll wrap up and take questions. Yeah? I know we're behind. Go ahead.